Hello. So I'm the next speaker. You may have noticed I've got a slight movement disorder. It is not Parkinson's, it's an essential tremor that gets worse with nerves, so, and coffee, but it will get better later with a drink, so perhaps come see me then and I won't be so affected. So my talk today is about a type of Parkinson's which is genetic. We know absolutely it's well proven, so I'm just going to explain a bit more about that. To begin with, if this works, maybe I push that button. Is it just the forward button? If my hand stops shaking. No. Oh, I'm just not pressing it hard enough. Okay, first of all, I just wanted to pose a question to the room. Who here would like to know what caused their Parkinson's? Okay. Would you still like to know what caused your Parkinson's if that means you've got family members who might be at risk? Yep. Okay. And if it means that there might be a better chance of curing that type of Parkinson's. Okay, obviously with that last question. So when we're working in a space where we know we've got a genetic form of Parkinson's, it informs the people, it gives people an idea of why me, but it has the convex, or the other side of it is, hang on, if it's affecting me, it might affect my siblings, it might affect my children, and people might have extra worries. So we do have to tread carefully. With Parkinson's, we've all heard today that it's caused as a result of many different things. And in this slide here, and hopefully, if I press it hard enough, press it at you, okay. I'm just focusing on that little bit in the middle, which is basically saying 5 to 10% of Parkinson's, as we know it now, are caused by single gene changes. Okay, this isn't what Justin was just talking about, where it's interactions from multiple genes. We know there's a handful of genes that if you get mutations in those genes, you will end up with Parkinson's. When we think about Parkinson's, and whether it's inherited, the things to think about are, did I get my Parkinson's quite young? So if we're seeing people getting Parkinson's in their teenage years, their 20s, their 30s, we're automatically thinking that's too young to have developed or been exposed to all those environmental effects, so we would think about genetics. We also might think about it when you've got a strong family history. The only problem there is that Parkinson's, as we know, it's the fastest growing neurological disorder, and some of that family history is still a combination of genes and environment. However, if those people in your family who have developed Parkinson's were on the younger side, that would give you an indication to think about asking your neurologist about genetic testing. So, with genetics, the type of genetics that we're talking about to do with Parkinson's, because there are different ways of inheriting genes, we are only talking about autosomal dominant and autosomal recessive. So the other thing I just wanted to say, you'll see these little QR codes in the corner. If you want to find out more about what's on this slide, if you shine point your camera at that QR code and then press it, it'll take you to the link that'll explain more about dominant and recessive. And you can just save that and come back and access it later. But I just needed to at least give you a basic introduction around genetics. And some of the genetics that results in genetic Parkinson's is autosomal dominant. But the type of genetics, what do I press? Oh, that one. Oh, okay, thank you. Of course. The type of genetic Parkinson's that I'm going to describe to you today is an autosomal recessive form. So what happens here is two parents come together, they are carriers, and those carriers have a 1 in 4 chance of producing a child with this form of pink 1 Parkinson's disease. Those carrier parents, as far as we're aware, are absolutely normal. They don't get Parkinson's. So that leads me on to the gene that I'm interested in studying, and I'll also explain why I'm interested in studying. It's called the pink 1 gene. That's a nice, easy gene to remember. Now, the pink 1 gene makes a protein called the pink 1 protein, so that's also easy. We all need pink 1, so we all have pink 1. Pink 1 is a good thing. We need it to make our cells function normally. However, if one of our genes does not make the correct type of pink 1 protein, that's okay, you're a carrier. But if both of your genes make an incorrect form of pink 1, you will get early onset Parkinson's disease under the age of 50. So if that can be very confronting and a bit surprising when a neurologist might see a young person in their 20s who's actually been having symptoms since the age of 12 or 13. And I'm sure everyone in this room can empathise with that situation because you have the lived experience of living with Parkinson's as it is, but imagine having to live with it from a much younger age. So luckily, from Justin's talk, he introduced this concept where you've got some genes that have a large impact, but they're very rare. And then you've got some uncommon genes that have been talked about in this today already, GBA being one of them, and LRRK2. And then there are a whole bunch of genes at the other end where you very commonly find variants. But single gene changes in those do not tend to cause Parkinson's. It's going to be multiple additive and how those interact with the environment. So underneath, you'll see the percentages. So what constitutes rare and what constitutes common. And what we find in our population here in New Zealand, the pink 1 gene, and this is why we're interested in it, the pink 1 gene isn't so rare. It is, if you have an allele frequency of less than 1%, that means less than 1 in 10,000 people would end up with pink 1 Parkinson's. But we know that the carrier rate in our Samoan, Tongan and Tokelauan populations, the carrier rate is nearer 1 in 16, which means we're talking about an affected rate of about 1 in 1,200, something like that. So this single pink 1 variant causes a change from leucine to proline at position 347. So it's a single amino acid change, and it causes this dysfunctional pink 1 protein. And as I said, it does seem to only find itself in the Pacific. This particular leucine to proline at 347, that's what L347P means, is only found so far in native Malay, in people from the Philippines, people from Guam, and then Samoa, Tonga, Tokelau, New Zealand by migration, and Hawaii by migration. So the numbers in pink there are the carrier rates, and the reason New Zealand is separated out from 1 in 34, so that's in Māori and Polynesians in New Zealand, the carrier rate's 1 in 34, but if we further stratify that, the Māori have a much lower carrier rate, only 1 in 137. So Hape didn't bring it here as much as it stayed in the islands. So we know that it's migrated probably, well, we assume because that's how we think the migration has worked from Southeast Asia into the Pacific, and whether it's through Melanesia or Micronesia, we haven't worked out. So it's obviously important in those populations, but it also teaches us something about Parkinson's for the wider population. And people have introduced the importance of mitochondria in cell health, and we know for a fact that mitochondria is the cause of the PINK1 Parkinson's. So what happens is PINK1 works together with a protein called Parkin, and what they do is they identify, label, and sort of take that cellular recycling or that mitochondrial recycling in the cell to fruition. And if your PINK1 isn't working, so if your quality control machinery, the PINK1 and the Parkin, aren't working, your defective mitochondria build up and build up and build up and eventually cause the cell to die. And because the dopamine-producing cells in our brain are very energy dependent, and what makes energy? Mitochondria. So that's why it has this extra need for energy, extra need for functioning mitochondria. When you don't have functioning mitochondria, those cells fall over the first. So whilst we have PINK1 all throughout our body, the rest of our body works, but where we see it affect people the most is when the dopamine cells die. So what can we do to maintain the health of the mitochondria for everyone in this room? And it does come back to a lot of the things that Bas had talked about in his talk. So minimising stress is a big thing. So physical stress, mental stress, emotional stress. Maximising rest, especially restful sleep. Exercising to your new limit, because exercise is important, but we can also get a bit compulsive. And we can maybe stress our mitochondria too much by, pushing yourself too far. So maybe don't exercise to total exhaustion. Eating clean whole foods and avoiding ultra-processed foods. And the link I'd like to reinforce here is that your diet actually is involved in the stress process, but at a cellular level, because certain foods can actually stress our cells, and healthy foods don't stress our cells. So diet is very important. Now the next big question, the elephant in the room, is why is it so hard to cure Parkinson's, even when we know what is causing it? So here we know PINK1 is causing this type of Parkinson's, and yet we still haven't got a cure for PINK1 Parkinson's yet. We're still working towards that. And this is where I draw on some previous experience, because I've only really started in Parkinson's research recently, in the last 3-4 years. I've previously worked in the areas of diabetes and metabolism research, and then cancer research. And what I've learned from my time in diabetes and cancer research is that there is a real difference in how you can make targeted therapies that target the disease in question. And if you've got a disease like cancer that is caused by the overgrowth or overactivity of something in the cells, then all you've got to do is knock down that overactivity. You know, you hit it hard. You think about chemotherapy. You hit it hard, you kill those cells, and you get rid of the cancer. If you've got other diseases like diabetes or Alzheimer's or Parkinson's that are, in the first case, they're caused by a loss of cells, somehow you've got to replace those cells. And it's not just as easy as getting rid of the overactive cells. You've got to either replace the cells or find another way around it. The other thing I would say here is that when you have cancer, people accept that taking chemotherapy is toxic. It's going to knock you around. You're going to feel absolutely crap for that time when you're taking chemo, but you know it's killing the cancer and then you'll get better afterwards. If you've got diabetes or Parkinson's, you are living the rest of your life with that condition the way it is now. So we have to be very, very certain that the drugs we're giving don't have toxicity, don't have really bad side effects, or if there are side effects, they're balanced by the benefits. Because someone is going to have to take those drugs for the rest of their life, not just for a short time. So it's much harder to work on diseases that are caused by losing cells. And what do we mean by a treatment versus a cure when cells die? Treatment is what we are kind of doing now in terms of levodopa. We are replacing the missing cell product. So in the Parkinson's brain, what is missing is the dopamine-producing cells. It's too hard to put back those cells just at the moment, although there have been some work done in the area with stem cells moving forward. But what doctors do is they prescribe dopamine. So that's treatment of symptoms. It keeps you going. It's not curing the disease. It's not replacing the cells. It's not stopping further cell loss. That relies on transplantation, as I said, perhaps gene therapy, or bypassing that blocked pathway that Justin talked about and trying to find another way around to make things work. So that's what we're working towards with Pink 1 Parkinson's. And I think I want to leave you with a message of hope, because we do live in exciting times. Like I say, I worked in cancer and diabetes for a long time, and I just happened to move over into the neurogenetic space because I wanted to work with lovely people like yourselves rather than with cells in a petri dish, even though I get less nervous working with cells in a petri dish. And from my time, so I started at the Department of Neurology in 2018, and it just happened to coincide with the fact that there are now gene therapy clinical trials. This is for genetic forms of disease. And even in the time from 2019 where there's this paper, and there's, if you click on that QR link, it'll take you to that paper. These are all the neurological disorders, the genes they're targeting, and how those genes have been administered. And now we actually have a handful of therapies out there that are actually FDA approved and being used. So gene therapy was one of the things that we could do, and it's one of the things that is working in other neurological diseases, so that holds hope. Just finishing off, we all talked about the fact that the tulip, well, Bas introduced the fact that the tulip was the symbol of Parkinson's worldwide. Now, I did a little bit of research on this, so it's because a Dutch horticulturalist called Van der Velde, he had a Parkinson's disease and he was a breeder of tulips. So he named this tulip in 1981 after Dr. James Parkinson. So that's why we have the tulip. And it's only since 1981. But as we know, Parkinson's isn't a single disease, and I don't see it being a monoculture of red tulips. I see it being a rainbow of colours. And in New Zealand, I see it not just being tulips, I see it being the hibiscus as well. So I think there's great hope. We're learning more. What we can learn from this disease, this form of Pink 1 Parkinson's, should also inform the rest of what we work on from the point of view of the mitochondria. And I know one thing I wanted to say at the beginning, because in Morris's talk, he opened with the fact that he had his pictures of his heroes up there, and I thought, oh, I don't have anything like that. But I thought about it, and it didn't take me long to think of this. This room is filled with my heroes, because and that's not, it's not the researchers, although they are wonderful, it's the people living with Parkinson's. You all had to go the extra mile to get here. I just had to get on my motorbike and work out where the Holiday Inn was. But you would have done so much planning to get here and maybe had some anxiety, and I really want to acknowledge that and thank you, because we work for you. Thank you.